Hi, it's Gary. Welcome to today's video. Let me ask you a question. How fast can you travel? On average, a human, we can walk at between 2 to 3 miles per hour. That's roughly 3 to 4 kilometers per hour. A cheetah, that can run between 50 and 80 miles an hour, or 80 and 130 kilometers per hour. But looking at light, well, it travels a little bit faster. In a vacuum, light and most other electromagnetic radiation, it travels at 186,000 miles per second. That's 299,792 kilometers per second. That's fast. It's so fast that the light from the sun takes about 8 minutes to reach Earth. Now, here we're talking about the speed of light in a vacuum. We will talk about it in some other materials later on. And this, it's a universal physics constant, and it's known by the letter C. In 1905, Albert Einstein published his special theory of relativity. In this, he stated that nothing could travel faster than the speed of light. So that means anything with a mass, and this includes most particles, they would get heavier and heavier as they approach the speed of light, and that when they reach the speed of light, they'd have an infinite mass, which essentially means they can never reach the speed of light. Now, part of this work, it led him to discover the equation E equals mc squared. And what that means is energy is equal to mass times the speed of light squared. Now, there's a lot to this equation, which we're not going to go into it. But for all intents and purposes, E equals mc squared is a good way at looking how mass and energy can work with each other. There's a long history with the measurement of the speed of light, and it dates back right the way to 1676, when measurements were taken using Jupiter's satellites. And that came up with the figure of 214,000 kilometers per second, so not that far off. There's been a number of other experiments. There was one in 1849 which used a toothed wheel. That came up with 315,000. Then throughout the 1900s, this figure, it was further refined using various different experiments. And then in the end, in 1983, that's when the value 299,792 kilometers per second was come up with. There was an experiment carried out back in the 1600s by Galileo. In his experiment, he had two people stand on two hills, and they were a mile apart. And each person had a shuttered lantern. The experiment was for lantern 1 to be unshuttered. Then when the person with lantern 2 saw the light from that lantern, they would unshutter theirs. And then when person 1 saw that return light from lantern 2, they'd record down the time it took from them opening their lantern to them actually seeing that return. Remember, this was only over a mile. This is what's called a two-way measurement. So it relies on the light going out and then coming back. In this experiment, the light, it was just too fast. They weren't able to calculate the time that it took. And we now know why, because we know how fast light travels. The one thing they were able to say from this is that the speed of light is at least 10 times faster than the speed of sound. This same two-way mechanism is still used today for measuring the speed of light. So a light pulse is sent out, reflects off a mirror or reflects off something else, and then it's returned. Now, obviously, nowadays we can use much longer distances. We've got very accurate timepieces. At the moment, it's not possible to measure the speed of light using a one-way pulse. We still have to use this two-way pulse. Why we can't use a one-way transmission? Well, it takes the same amount of time to send the light as it would do to send the signal saying, I'm sending the light. So you wouldn't really be able to measure it. Now, there are limitations with the speed of light, and knowing these, they can really help, especially when we come into things like communications. If we look back to the Apollo missions to the moon, they were in the 1960s. There was a 1.225 second delay between a message being sent from Earth and being received at the Apollo craft near the moon. So that means if you want to ask a question, you've got a delay of 3 seconds. And that's on top of the time that it takes them to think about and get back to you. That doesn't seem too big, does it? But let's start thinking about missions to Mars. Depending on the location of Earth and Mars, a message can take up to 20 minutes to get from Earth to a robot on Mars. So that means if you're doing a two-way discussion, if you're asking for some information, it's going to take 40 minutes in delays alone to get that information. So imagine you're going to ask someone a question. You're going to ask the robot a question. You ask it. You hit enter on your keyboard. It sends the message. You then sit there twiddling your thumbs. It takes 20 minutes for that message to get to Mars. The robot or the person, they do their processing. They then send you the message back. And again, you're still twiddling your thumbs because it's going to take another 20 minutes for that message to get back. Now, I'd find that quite frustrating, I will be honest. So I think it's amazing how they actually are able to manage all these devices. As I said previously, when we talk about the speed of light, we usually are talking about the speed of light in a vacuum. Now, light actually does travel at different speeds in different materials. It usually travels slower in other materials. It usually travels slower in other materials when compared with a vacuum. And the percentage slower, it's known as the refractive index. The refractive index for air is 1.0003. So light, it travels about 90 kilometers a second slower in air than it does in a vacuum. Seems like a lot, doesn't it? But not when we're looking at the speeds involved, obviously. The refractive index for glass, it's 1.5. So in glass, light travels at 200,000 kilometers per second, as opposed to the 299,792 kilometers per second in a vacuum. Quite a lot slower. But in practical terms, certainly for us on Earth, our glass windows, even glass cubes, they're not that thick, so the difference is just too small to be measurable. But this does come in useful when you're using things like a fibre optic cable. A good example of this, the Earth, it's got a circumference of about 40,000 kilometres. So the time for light to travel halfway around the world, if it was in a vacuum, is 67 milliseconds. That's fast. But we don't send light like that. It has to go through fibre optic cables, and they have limitations. It goes through the cable, which is made from a glass-like material. It also has to go through electronic switches and signal boosters. They all delay it, and we need to be able to add that delay. When we look at it, it means that the time to go through the fibre optic cable, it's roughly 35% slower than if it was going through a vacuum. So that means that the light to travel halfway around the world, instead of taking 0.67 milliseconds, it's going to take roughly a second. Yes, I know, it doesn't sound like a lot, but engineers need to be aware of this because it can make a difference when you're looking at the latency of signals. Because the speed of light is so big, when we start to look at astronomical distances, things like the distances between stars, it just becomes so hard to visualize it. This is why we often hear of something called a light year. That's the distance that light can travel in 1 Earth year. This works out to be roughly 9,461 billion kilometers, or 5,879 billion miles. It's a big distance. It's just so hard for us to think about those numbers. That's where the idea of the light year comes in. So if we take a look at our nearest star, Proxima Centauri, that's roughly 4.2 light years away. Now, if we're going to talk about it in numbers, that's 39,736 billion kilometres, or 24,691 billion miles. I don't know about you, I'd rather hear the figure 4.2 than all those billions. The speed of light, it also opens up lots of other questions, and they're things I'm going to cover in videos further down the line. And, some of the questions around this is things like, how does GPS work relies on the speed of light. Would time travel be possible? That's a really interesting thing, and that's one of the things I enjoy sci-fi programs, so that's a video that I'd like to make. But there's lots of other things where the speed of light is involved in. I hope you've enjoyed this video. I've tried to keep it brief, so I've cut out a lot of the research that I've found. Speed of light is so interesting when you start digging into it. I know it sounds really boring, but once you get into the details, it's amazing how interesting it can be. Are there any things you'd like me to be looking at as part of this speed of light discussion? Any particular things that you think, oh, maybe things like, say, the distances, it'd be interesting maybe to dig deeper into that. Or GPS, as I say, I'm already planning a video around GPS. Please drop your ideas and comments in the comments down below. Please hit the thumbs up button. Every time you like, every time you comment, just helps with the YouTube algorithm. If you haven't already, please subscribe to my channel so that you can get new videos as I release them. I'll talk to you again soon.